The gravitational force is a force that arises from the interaction between two objects that have mass. We can consider it to arise from the mass of one object interacting with the gravitational field of the other object. This interpretation is consistent with the units of gravitational field, which you recall are newtons per kilogram. This is the equation for the gravitational force acting on a point particle. It depends on the mass of the point particle and the gravitational field experienced by the point particle. This is not the gravitational field of the point particle itself, but rather the gravitational field from the other objects in the system that interact with the point particle. Because mass is always a positive scalar, the direction of the gravitational force acting on a point particle is the same as the direction of the gravitational field experienced by the point particle. The gravitational force between two point particles A and B can be considered to arise from the interaction of the mass of particle A and the gravitational field of particle B. Alternatively, we could consider this gravitational force to arise from the interaction of the mass of particle B with the gravitational field of particle A. Either interpretation gives the same final expression, as expected from Newton's third law. In these calculations, we have determined the magnitude of the gravitational force between A and B. We know that the direction of this force will pull the two objects together. The gravitational force acting on point particle C in this system depends upon the gravitational field experienced by this point particle. This gravitational field arises from point particles A and B. We have already calculated this gravitational field, and if the masses of particles A and B are identical, the net gravitational force acting on particle C is in the negative direction along the y-axis. Now let's calculate the gravitational force that exists between a uniformly dense rigid rod, denoted by A, and a point particle, denoted by B. Specifically, let's calculate the gravitational force exerted by point particle B on the rigid rod. We can consider this gravitational force to arise from the interactions of infinitesimally small bits of mass in the rigid rod and the gravitational field of the point particle. If these bits of mass are infinitesimally small, we can treat them as point particles and use our equation for the gravitational force of a point particle to determine their interaction with the gravitational field of particle B. Let's begin by calculating the magnitude of this gravitational force. We know that since mass is always positive, the gravitational field of particle B will point toward particle B. Let's define an x-axis for our system with a positive direction pointing from the rod to the point particle. That is, the positive direction for the x-axis will point to the right in the figure. The direction of the gravitational field of point particle B is thus in the positive x-axis direction. The direction of the gravitational force experienced by each infinitesimally small bit of mass in the rod is thus also in the positive x-axis direction. The total gravitational force experienced by the rod is the integration of the contributions from the infinitesimally small bits of gravitational force acting on each infinitesimally small bit of mass in the rod. Many of the variables in this integration, including the unit vector, are constant and can be taken outside the integral. What remains is a familiar integral involving the variables dm and r. As we have done before, we can express dm in terms of dr using the linear mass density of the rod. Recall that since the rod is uniformly dense, the linear mass density of the rod is constant at every point and can also be taken outside of the integral. What remains is an integral involving only the variables dr and r. The limits of this integral are determined by the possible positions of the infinitesimally small bits of mass in the rod. The smallest value for r in this equation is d, and the largest value is d plus L. These limits denote the closest and farthest any constituent point particle in the rigid rod can be to particle B. The final integral is relatively straightforward. As expected, the direction of the gravitational force acting on the rod is in the positive x-axis direction. In other words, the rod is pulled toward the point particle. We arrive at our final expression by substituting the expression of the linear mass density of the rod. Since the rod is uniformly dense, the mass density is simply the mass of the rod divided by the length of the rod. Alternatively, we could have considered the gravitational force to arise from the interaction of the point particle with the gravitational field of the rigid rod, which we determined earlier. Recall that since the mass of the rod is positive, the gravitational field of the rod points toward the rod, which in this case is in the negative x-axis direction. As expected, the magnitude of the gravitational forces determined through these two calculations are the same. The directions are different, however, due to Newton's third law. This figure combines everything that we have learned about gravity. Please keep it in mind as you continue to review your understanding of gravity and as you learn new interactions in this course. Gravitational potential and gravitational potential energy are related to each other by our equation for the gravitational potential energy of a point particle. We can use integral calculus to apply this equation to systems that aren't point particles. Gravitational field and gravitational force are related to each other by our equation for the gravitational force acting on a point particle. We can use integral calculus to apply this equation to systems that aren't point particles, as we just saw. Gravitational potential energy and gravitational force are related through differentiation and integration. This works because gravitational force is a conservative force. Please note that when integrating the gravitational force, we determine only a change in gravitational potential energy, not the absolute value of the gravitational potential energy. Gravitational potential and gravitational field are related through differentiation and integration. Please notice that when integrating the gravitational field, we determine only a change in gravitational potential, not the absolute value for the gravitational potential.